The industrial production of nougat is a combination of confectionery science and modern manufacturing technology. Before a new batch of nougat is made, the entire process from raw material preparation to environmental control must comply with strict standards. First, basic ingredients such as sugar, glucose syrup, water, fat, mainly palm oil or shea oil, dry milk powder, cocoa, and egg whites must be imported into the factory in separate specifications. Dry ingredients such as sugar and milk powder are transported to a closed silo system via pneumatic conveyors, where they are stored in a strictly climate-controlled environment. This system ensures that no dirt or impurities from the outside environment can enter. Each batch of raw materials is labeled with a barcode for traceability, allowing the factory to check parameters such as the purity and color of the sugar using laser measurement technology. Liquid ingredients such as glucose syrup and oil are pumped into heat-jacketed stainless steel tanks. These tanks keep the ingredients at the correct temperature to ensure the right viscosity during production. For example, glucose syrup is maintained at around 40 degrees Celsius to prevent crystallization, while oil needs to be heated and stirred constantly to avoid separation. After quality control, the ingredients are transferred to the production area, which is maintained at the optimum humidity and temperature to ensure the correct nougat texture. All equipment in this area is thoroughly sterilized before operation. The sugar, syrup and water mixture is heated to around 115 to 120 degrees Celsius using indirect steam to achieve the ideal consistency, but not too hot to avoid caramelization. Sensors continuously monitor the temperature, adjusting the syrup quantity or cooking temperature to ensure the mixture is within specification. Once the desired temperature is reached, the mixture is cooled to around 70 to 80 degrees Celsius before egg whites or albumin are added. If the background temperature is too high, the egg proteins will denature, affecting the texture of the nougat. This is followed by the foaming stage, where the mixture is whipped using a high-powered air blower. Sterile air is introduced under pressure to create a stable foam, giving the nougat its characteristic softness and elasticity. Parameters such as temperature, pressure and air, liquid ratio are all automatically controlled by the PLC system, ensuring the uniformity of the final product. During the production of Mars chocolate bars, technical parameters are measured by flow density meters. The system automatically calibrates the airflow, syrup, or alerts when necessary. Operator intervention. At this point, cocoa powder and dry milk are added to the base, giving the nougat its unique color and rich, melting flavor. Once the nougat mixture has been shaped and cooled, the next step is to shape the product. The mixture is poured onto a stainless steel conveyor belt, forming a continuous layer approximately 2 to 3 centimeters thick. The nougat layer is fed into a cooling tunnel, where it is gradually cooled from approximately 60 degrees Celsius to below ambient temperature by circulating cold air. This system helps the nougat maintain a uniform softness without hardening the surface too quickly or causing condensation. Once the nougat layer exits the tunnel, it enters the cutting station. Here, a cutter rotates in sync with the conveyor belt speed, dividing the nougat layer into small strips, each of which becomes the base of a Mars chocolate bar. These strips are further broken down using either a straight knife or an ultrasonic cutter to produce uniformly sized pieces. A visual inspection system ensures that each piece is the correct length, width, and height, with any product that does not meet the standard being automatically rejected. After shaping, the nougat pieces are prepared to receive the caramel layer. Before the caramel is deposited, the nougat pieces are spaced and aligned using a lane switching system to help them move evenly through the next stage. Once the temperature has stabilized, the nougat is ready to be coated with caramel, a layer that provides a unique blend of texture and flavor. Producing caramel on a large scale is a delicate process that requires close control. This stage incorporates continuous cooking, emulsification, temperature regulation, and precise deposition to ensure the caramel reaches the desired consistency. The caramel in Mars bars is more than just a coating, it plays a crucial role in the product's taste. Made from sugar, glucose syrup, sweetened condensed milk, or milk solids, fat and emulsifiers. The caramel must have the right consistency, not too hard to make it difficult to chew, but not so runny that it loses its smooth texture. Caramel production begins in a dedicated cooking area, separate from the nougat line but working in unison to maintain a steady production rate. All ingredients are stored near the cooking area, with sugar and milk powder flowing by gravity from silos into a pre-mixing system. Glucose syrup and fat are pumped in from temperature-controlled tanks, while emulsifiers such as monoglycerides and diglycerides are added by metering pumps to ensure a smooth texture. Before the caramel enters the main cooker, the mixture is preheated in a stainless steel tank with a heat jacket to a uniform temperature of around 70 to 80 degrees Celsius. This stage allows the ingredients to blend completely, creating a stable base before entering the vacuum cooking stage. Here, the mixture is heated rapidly in a low-pressure environment, allowing the water to evaporate at a lower temperature without burning the sugar or overheating the milk. This system maintains a temperature of 115 to 120 degrees Celsius, allowing the caramel to reach a final water content of around 6 to 8% with a sugar concentration of 80 to 85 bricks, ensuring a smooth and stable coating on the nougat bar. During the production of Mars chocolate bars, the specifications are measured by a flow density meter, an automatic system that calibrates the airflow, syrup, or alerts when operator intervention is required. At this point, cocoa powder and dry milk are added to the base, giving the nougat its unique color and rich, melting flavor. These ingredients are added by a continuous powder feeder, which measures the dry material by volume, which is evaluated by air before it leaves the mixer. The mixing takes place in a closed paddle mixer with gentle agitation, ensuring that the foam structure is maintained. The result is a warm, chocolate-colored nougat with a light, stable texture and moderate elasticity. Once the nougat mixture is formed, it needs to be shaped and cooled. The mixture flows from the mixer onto a stainless steel conveyor, forming a continuous sheet about 2 to 3 centimeters thick. This sheet passes through a cooling tunnel, where the temperature is gradually reduced from about 60 degrees Celsius to just below ambient temperature. The cooling system uses circulating air, partitioned into sections to ensure that the nougat is cooled evenly without condensation or surface hardening too quickly. As the nougat sheet exits the tunnel, it is cut across by a cutter that rotates in sync with the conveyor speed. These narrow strips will become the base layer of the Mars chocolate bar. The strips are then cut lengthwise using a straight line knife or ultrasonic cutter, forming uniform rectangular nougat sections. A vision system scans each section to check the dimensions, length, width and height, with automatic rejection of pieces that are out of tolerance. The finished nougat pieces are ready to receive the caramel layer. Before the caramel is deposited, the nougat pieces are aligned using lane diverters and product guides, ensuring that each bar progresses smoothly through the next stages. They then enter the buffer zone, where the temperature is stabilized in preparation for the caramel coating. The caramel layer is one of the signature ingredients that gives the Mars bar its unique texture and flavor. Producing caramel on a large scale requires a specialized process that combines continuous cooking, emulsification, temperature control and precise deposition, ensuring the caramel has the right consistency, not too hard but not too runny. The caramel for Mars bars is made from a balanced combination of glucose syrup, sugar, sweetened condensed milk or milk solids, and a blend of fats and emulsifiers. This mixture is cooked to a certain consistency, which helps it hold its shape during packaging but also flows easily when bitten. Caramel production begins in a dedicated cooking area, synchronized with the nougat line to maintain a steady flow. Ingredients such as sugar, milk powder, glucose syrup and fat are introduced via a temperature-controlled metering system and pumps. Emulsifiers such as monoglycerides and diglycerides are added precisely to ensure a smooth texture. Initially, the mixture is mixed in a stainless steel preheating tank at around 70 to 80 degrees Celsius, which homogenizes the ingredients before being fed into the main caramel cooker. From here, the mixture is continuously pumped into a vacuum caramel cooker, where it is heated quickly and evenly, while excess water is removed to control viscosity and solids content. Inside the cooker, The pressure is reduced to allow the water to evaporate at a lower temperature, avoiding burning the sugar or overcooking, which can result in bitter milk or an unstable texture. The caramel mixture is heated to approximately 115 to 120 degrees Celsius, reaching the appropriate density with a residual water content of approximately 6 to 8% and a sugar concentration of approximately 80 to 85 bricks. Once the chocolate coating is complete, the Mars bars undergo a thorough cooling process to ensure the required consistency of the texture. A DuPont sensor and fan system works in concert with the refrigeration units to maintain a stable environment, preventing condensation on the surface of the chocolate. Each bar spends approximately 5 to 8 minutes in the cooling tunnel before emerging with the finished coating, ready for packaging. In the next stage, the Mars bars are fed onto an accumulation conveyor to prepare for the high-speed packaging process. Each product passes through a flow packer, where the film is pulled off, forming a protective coating, which is then sealed at both ends and trimmed. These packaging machines are capable of processing hundreds of bars per minute, ensuring that each product is weighed and scanned before moving on to the final packaging conveyor. At this point, the product looks exactly like a Mars bar on a retail shelf. But the process is not over yet. The next step is secondary packaging, where the bars are assembled into cardboard boxes or shipping trays ready for distribution. This is a critical step in protecting the product, ensuring traceability, and optimizing the supply chain. The packaging line operates on an industrial automation system, processing millions of units per day. First, the Mars bars travel on a conveyor belt to a flow packer. Here, a continuous roll of printed film is fed into the system, where folding arms and heat-sealing jaws form the final seal. The temperature of the jaws is tightly controlled to ensure the wrap is sealed without distorting the material. Mars uses a multi-layered film that not only protects the product from oxygen and moisture, but also gives it a premium feel when held. The inner layer is a heat-sealable polymer. The middle layer can be aluminum or a metallic coating, and the outer layer contains the brand's illustration. The system sensors check the accuracy of the print, ensuring that each bar's logo is aligned. Any products with printing errors are automatically rejected. After packaging, Mars bars are weighed using a dynamic weighing system to ensure they are within tolerance. If there is a discrepancy in the weight, the product is automatically rejected. Next, each bar is passed through a metal detector to ensure that no foreign matter has entered the production process. Some plants also use X-ray scanners to detect non-metallic contaminants. Once the bars have passed all inspection steps, they are transferred to a packaging station. Depending on the retail format, the bars may be grouped into trays or shipping cartons. Robotic systems arrange the products in an optimal pattern, then seal them with hot melt adhesive or a flap. Each box receives a printed label with a batch code, production date, and a QR code for inventory tracking. Finally, the boxed product is delivered to the palletizing station. Robotic palletizers use mechanical arms or vacuum clamps to stack each box onto a pallet in the correct shape. Some systems also add cardboard between layers for added strength. Once the pallet reaches its standard height, usually around 1.6-1.8 meters, it is wrapped in stretch film to secure the entire product. Pallet labels then contain SKU information, product quantity, gross weight, destination, and identification codes to support the inventory management process. The factory's internal tracking system plays an important role in managing products after they are manufactured. Each pallet before entering the warehouse is labeled with a thermal printer and verified with a barcode scanner to ensure traceability. This is part of a centralized manufacturing execution system, MES, which tracks all products in real time. Each box, candy bar, and pallet contains data encoded in a barcode or RFID tag, including information about the production line, ingredients, and processing conditions. This traceability is key to complying with food safety regulations and internal quality control. Mars plants use air circulation to maintain a stable temperature inside the warehouse, while insulation and vapor barriers help block outside influences. The warehouse is operated by automated guided vehicles, AGVs, or forklifts with real-time positioning systems. When storing pallets, The warehouse management system prioritizes the goods. High-volume products are placed near the shipping area, while seasonal or export goods are stored deeper. Because Mars factories operate on a just-in-time production model, inventory is typically held for only a short period of time, typically less than a week, before being shipped to meet distributor orders. When a shipping request is made, the warehouse team receives a list. Digital picker, a GV or warehouse staff will pick up the pallet, verify it with a handheld scanner and transfer it to the loading area. Before loading the product onto the truck, each shipment is inspected to ensure that the order matches the specifications, is within the allowable temperature range and has an intact pallet wrap. Refrigerated trucks or climate-controlled vehicles are often used for long-distance shipping or deliveries to areas with high ambient temperatures. The loading process is performed using a dock leveling system and rollers to ensure smooth movement and avoid tipping over. During transportation, each shipment is monitored with a temperature recorder, recording data at certain intervals. When the goods are delivered, this data is checked. If there is any deviation from the acceptable level, the shipment may be subject to further inspection or rejection. Mars also monitors customer feedback, market audits and internal quality checks. Samples from each production batch are kept in climate-controlled storage for shelf life testing. These samples are periodically monitored for appearance, flavor, texture, and microbiological stability to ensure that the product meets standards even after leaving the factory. In addition, Mars has a dedicated quality control laboratory where product samples are physically and chemically analyzed. Parameters such as moisture, fat, sugar crystallinity, pH, and emulsion stability are all tested using advanced measuring equipment. Sensory teams are trained to evaluate product aroma, texture, and aftertaste, and auditors conduct regular tests according to export standards. Some facilities also use accelerated aging chambers to simulate short-term shelf life, helping to predict the impact of packaging or formulation changes before they hit the market. In addition to mass production, Mars also operates pilot plants and R&D laboratories where new recipes, manufacturing methods, and equipment calibrations are continually tested and refined before being rolled out globally. Whether Mars bars are produced in the United States, the United Kingdom, or any licensed facility, they must adhere to strict standards to ensure consistent product quality. This requires detailed documentation, real-time data comparisons, and synchronized updates across plants to maintain consistency in appearance, taste, and texture. Pilot plants are typically located adjacent to the main production facility, serving as miniature test beds for the actual manufacturing process. Here, equipment such as miniature mixers, settlers, incubation tanks and coaters are used not only to experiment with new flavors or different candy bar formats, but also to test ingredient changes when adjusting raw materials, such as cocoa or emulsifiers, to suit market conditions and regional regulations. A new variation of a Mars bar, such as one with a cookie layer or a salted caramel flavor, may go through dozens of test batches before it goes into mass production. Each test batch is evaluated not only on consumer preferences, but also on how it performs on the actual production line. Does the caramel flow smoothly as it moves down the conveyor belt? Does it retain its shape through the cooling tunnel? Does the chocolate coating crystallize properly? These questions are answered through data from digitally recorded test runs and used to build predictive models before large-scale deployment. Today, digital simulations are widely used in manufacturing testing. These tools help model the fluid dynamics, thermal behavior, and mechanical stresses on raw materials during processing, cooling, and transportation. This allows engineers to make dozens of line improvements without touching physical equipment, accelerating innovation safely and efficiently. Once a new manufacturing process is approved, Mars Global Standardization Team prepares adjustment packages that include updated specifications, manufacturing procedures, equipment calibration charts, and software updates. These documents are then sent to regional manufacturing centers, accompanied by remote training sessions or on-site visits to ensure smooth implementation. This global synchronization ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, your experience is completely consistent, From the sound of the chocolate cracking, to the chewiness of the caramel, to the speed at which the nougat melts, chocolate doesn't begin its journey in a factory, but in cocoa farms located in the tropics around the equator. Countries like Côte d'Ivoire, Ghana, Brazil, and Indonesia are the world's leading cocoa producers. The hot, humid climate, rich soil, and good drainage are ideal for growing Theobroma cacao trees, which produce cocoa pods containing cocoa beans, the main ingredient in chocolate. Harvesting is done entirely by hand. Farmers use machetes or curved knives attached to long poles to cut off the ripe pods without damaging the tree. Each mature tree can produce 20 to 30 pods per year, and because cocoa does not ripen all at once, the harvest lasts for months. After harvesting, the pods are split open by hand, leaving the beans still surrounded by a white pulp, ready for fermentation, the first step in developing the characteristic flavor of chocolate. Fermentation takes place on farms or in collection centers. The beans are placed in wooden crates or piled up, covered with banana leaves, to stimulate the activity of yeast and bacteria. These microorganisms convert the sugars in the pulp into alcohol and acid, raising the temperature to around 45 to 50 degrees Celsius. Under the influence of enzymes, the internal structure of the beans changes, reducing bitterness and forming complex flavor precursors. The process usually lasts 5 to 7 days, during which the beans must be turned regularly to ensure uniform oxidation. If not fermented enough, the flavor will be bland, while if too much can lead to excessive sourness or bitterness. Large chocolate manufacturers, while not fermenting their own beans, often work with their cocoa suppliers to ensure tight control over the process. Some companies even require pH and temperature testing to ensure consistent quality. Once fermentation is complete, the beans are spread out to dry on canvas or bamboo racks in the sun. This is an important step in stabilizing the flavor before the beans are collected and processed into industrial cocoa. Pilot plants are often built next to the main production facility, acting as miniature laboratories for the actual production process. Here, equipment such as miniature mixers, settlers, tempering tanks, and coaters are used not only to test new flavors or different bar formats, but also to test how ingredients change when adjusting raw materials, such as cocoa or emulsifiers, to suit local market conditions and regulations. A new variation of a Mars bar, such as one with a cookie layer or a salted caramel flavor, may go through dozens of test batches before it goes into mass production. Each test batch is evaluated not only on consumer preferences, but also on how it performs on the actual production line. Does the caramel flow smoothly as it moves down the conveyor belt? Does it retain its shape through the cooling tunnel? Does the chocolate coating crystallize properly? These questions are answered through data from digitally recorded test runs and used to build predictive models before large-scale deployment. Today, digital simulations are widely used in manufacturing testing. These tools help model the fluid dynamics, thermal behavior, and mechanical stresses on raw materials during processing, cooling, and transportation. This allows engineers to make dozens of line improvements without touching physical equipment, accelerating innovation safely and efficiently. Once a new manufacturing process is approved, Mars Global Standardization Team prepares adjustment packages that include updated specifications, manufacturing procedures, equipment calibration charts, and software updates. These documents are then sent to regional manufacturing centers, accompanied by remote training sessions or on-site visits to ensure smooth implementation. This global synchronization ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, your experience is completely consistent. From the sound of the chocolate cracking, to the chewiness of the caramel, to the speed at which the nougat melts, chocolate doesn't begin its journey in a factory, but in cocoa farms located in the tropics around the equator. Countries like Côte d'Ivoire, Ghana, Brazil, and Indonesia are the world's leading cocoa producers. Their hot, humid climates, rich, well-drained soils, and abundant nutrients make them ideal for growing Theobroma cacao trees, which produce pods containing cocoa beans, the main ingredient in chocolate. Cocoa harvesting is done entirely by hand. Farmers use machetes or curved knives attached to long poles to cut off ripe pods without damaging the tree. Each mature tree can produce 20 to 30 pods per year. And because cocoa does not ripen uniformly, the harvest lasts for several months. After harvesting, the pods are split open by hand, leaving the beans still surrounded by a white pulp, ready for fermentation, the first step in developing the characteristic flavor of chocolate. Fermentation takes place on farms or in collection centers. The beans are placed in wooden crates or piled up, covered with banana leaves to stimulate the activity of yeast and bacteria. These microorganisms convert the sugars in the pulp into alcohol and acid, raising the temperature to around 45 to 50 degrees Celsius. Enzymes change the internal structure of the beans, reducing bitterness and forming complex flavor precursors. This process typically lasts 5 to 7 days, during which the beans must be turned regularly to ensure uniform oxidation. Insufficient fermentation will result in a bland flavor, while excessive fermentation can result in an overly sour or bitter taste. Large chocolate manufacturers, while not fermenting their beans themselves, often work with their cocoa suppliers to ensure tight control over the process. Some companies even require pH and temperature testing to ensure consistent quality. Once fermentation is complete, the beans are spread out to dry on tarps or bamboo racks in the sun. This is an important step in stabilizing the flavor before the beans are collected and processed into industrial cocoa. The roasting of cocoa beans takes place in a rotating stainless steel drum, where the beans are exposed to heat directly or indirectly through a circulating stream of hot air. Temperature sensors mounted inside the drum monitor the temperature of the beans, the surrounding air, and the exhaust air temperature, ensuring each batch is roasted to the correct standards. The operator can adjust the rotation speed, airflow, and heat intensity via the PLC control interface to control the roasting process. The first stage of roasting occurs at around 100 degrees Celsius, mainly to remove any remaining surface moisture on the beans, lasting 5 to 10 minutes. The beans then enter a browning stage where the Maillard reaction takes place, creating hundreds of flavor compounds, from nutty to caramel, that contribute to the complexity of the chocolate. This stage takes about 10 to 15 minutes with the bean temperature rising to 120 to 140 degrees Celsius. The final stage, called the developing or finishing stage, raises the bean temperature to around 135 to 150 degrees Celsius depending on the desired flavor profile. This is an important step even though it only takes 2 to 5 minutes. Too short and the chocolate may lack depth of flavor, and too long and the product may burn or become too bitter. Advanced factories use infrared cameras and heat probes to monitor every second to ensure optimal results. After roasting, the cocoa beans must be cooled quickly to stop further cooking. This usually takes place in a cooling tray or drum system, where cold air is blown through by high-speed fans. In addition to cooling, this process also helps to harden the bean shell, preventing condensation or affecting the storage quality. At this point, the beans are dark brown, crispy and have a characteristic aroma, but there is still an outer shell that needs to be removed to get to the inside. The next stage is winnowing, a mechanical process that separates the shell from the cocoa nibs by grinding and air sorting. In large factories, the cocoa beans are passed through a primary crusher to crack them into small pieces, then transferred to a winnowing system. The airflow is adjusted to retain the heavier nibs, while the lighter shells are discarded into a waste hopper. The end result is pure cocoa nibs, rich in color and full of flavor. This is the base for making chocolate liquor, not a beverage, but a paste-like mixture of finely ground cocoa. Production begins with the cocoa nibs being fed into a pre-grinder or impact mill, where steel blades or stone rollers break up the beans. Frictional heat melts the cocoa butter, transforming the mixture from a coarse powder to a smooth paste. In this first stage, the particle size is reduced to about 80 to 100 microns, and the cocoa liquid is held in heated vats for further processing or sent directly to refining. Refining further reduces the particle size, creating the smooth, velvety texture of the chocolate. This is done using a ball mill or a 5-roll refiner. in which 5 steel rollers rotate at different speeds to grind the cocoa to 15 to 25 microns. At this size, the cocoa and sugar particles are so small that the tongue cannot distinguish them, giving the chocolate its characteristic smooth, creamy texture. In sweet chocolate factories, sugar is added at this stage of refining. The sugar is pre-ground to ensure a uniform particle size, then mixed with chocolate liquor to form the base for further processing. Depending on the recipe, some ingredients such as milk powder, vanilla, lecithin are also added at this stage. These ingredients are weighed and dosed precisely by automated systems to ensure that each batch of chocolate adheres to the standard recipe. After refining, the chocolate mass still has a dry, powdery feel. To turn it into a liquid with high viscosity, smooth surface, and stable flavor, it must undergo coning, a stirring and sifting stage that lasts from several hours to several days. Coning takes place in large heated tanks, equipped with rotating arms or heavy granite rollers. Its main goals are to improve flavor by oxidizing volatile acids, smooth the texture by evenly distributing the fat, and increase viscosity by removing excess moisture and unwanted compounds. The process is divided into 3 stages. Dry cone, the mixture is still dense and crumbly. Soft cone, the mixture becomes more runny. And liquid cone, completely liquid. Each chocolate recipe will have a different cone setting time. For example, milk chocolate will typically require a longer cone setting time to balance the milk solids and sugar, while dark chocolate with a high cocoa content may undergo a shorter cone setting time to retain its natural flavor and characteristic acidity. During this stage, temperature, pressure, and oxygen flow are all closely controlled. Some factories use closed-loop conching systems with nitrogen blankets to limit oxidation, while others use vacuum systems to remove unwanted volatile compounds. After hours of stirring and grinding, the chocolate mixture reaches a smooth, rich aroma. It flows like a thick liquid with a mature, balanced flavor. However, to stabilize the texture before packaging, the mixture needs to undergo a tempering process to control the crystallization of cocoa butter. Cocoa butter can form many different crystal forms, but only one type provides a final product with a smooth surface. Crisp crispness, ideal melting ability and stable shelf life. Therefore, the mixture needs to be precisely controlled in temperature. The tempering process takes place in specialized machines that continuously control the flow and temperature. First, the mixture is heated to around 45 degrees Celsius to completely dissolve any old crystals. The liquid is then cooled to 26 to 28 degrees Celsius, while a stirring system works to help the desired stable crystals begin to form. Once enough of these crystals have appeared, the mixture is gently heated again to around 32 degrees Celsius, allowing the stable crystals to be retained and eliminating unwanted structures that could cause efflorescence or affect the texture later. Once the product has cooled and solidified completely, it is transferred onto a conveyor belt to enter the quality control area. Here, a vision system scans each product for defects such as uneven surfaces, cracks, inconsistent colors, or signs of efflorescence. Non-conforming products are automatically removed from the line. In many plants, these defective products can be remelted, re-tempered, and reused in the next batch to minimize waste. From this point, the finished product moves to packaging. The packaging type chosen depends on the product format, individual bars, pre-formed shapes, or bulk. For single bars, the packaging line is designed to handle a large number of products per minute. Each bar is fed through a high-speed packaging machine, where the folds are cut and the wrap is heat-sealed with high precision, ensuring synchronization with the production flow and avoiding jams, tears, or misalignment. Packaging materials may include metallized film, wax paper, aluminum foil, biodegradable or composite materials, depending on product storage requirements, local environmental regulations and shelf life goals. Some manufacturers also use oxygen scavengers or atmospheric sealing systems to extend product freshness, especially for long-lasting packaged items. After packaging, the products are grouped into cartons or larger boxes using robotic systems. These automated arms identify product orientation, using suction fingers or gripping mechanisms to accurately place each product into a retail box. Display tray, or shipping container. The outer carton is then sealed, labeled, and scanned to ensure accurate barcode, weight, and expiration date information. The next stage is palletizing, where cartons are arranged and secured on shipping pallets in the most optimal way to utilize space and minimize stress on the lower layers. The pallet is then shrink-wrapped using rotating arms or heat tunnels before being labeled with shipping information, lot numbers, and destination. The entire manufacturing process is digitally recorded in the factory's quality control system, including raw material source, roasting and grinding parameters, tempering temperature, molding time, inspection timestamp, and final results. If a problem arises during distribution or retail, the factory has full traceability to determine exactly when the product was manufactured. Pallets of finished product are transferred to temperature-controlled storage, typically maintained at a constant 16 to 20 degrees Celsius to avoid melting, blooming or flavor deterioration. Humidity is also maintained below 60% to ensure product and packaging quality. Some specialty products, such as milk or white chocolate, are also stored under limited light conditions to prevent discoloration from UV rays. Finally, the product is shipped on a schedule that suits distribution needs. Orders are sorted by destination, retailer or distributor, and then transported by truck, ocean container or cargo plane. In some cases, temperature data loggers are placed inside the shipment to confirm that the climatic conditions remain within acceptable ranges throughout the entire shipment. Even after the product leaves the factory, it remains closely linked to the production process. Quality checks, retailer feedback and customer feedback can all be traced back to the shift and equipment used. Manufacturers often conduct shelf life simulations, flavor degradation tests and packaging durability analyses to ensure that the production process is effective over the long term. From raw materials to finished products, the entire system is geared not only towards efficiency, but also to repeatability and tight control. Industrial chocolate production functions as a laboratory, where rigorous technical processes meet the subtleties of sensory art. It is this combination of technical precision and creativity that makes chocolate one of the most exciting sectors of the global food industry. Even after the product leaves the production line, logistics continue to play a critical role, ensuring that the chocolate reaches the shelf in optimal condition. Maintaining quality throughout transportation, storage, display, retail, and final consumption. This sophisticated chain of processes is managed by state-of-the-art logistics, environmental controls, and close coordination between all links in the supply chain. Quality assurance occurs not only during production, but also throughout storage and transportation on a global scale. Once produced, packaged chocolate is placed in temperature-controlled storage areas within the factory's distribution department. These areas are closely monitored to protect the product from deterioration. The ideal temperature for storing finished chocolate is typically between 16 degrees Celsius and 20 degrees Celsius, with humidity maintained below 60%. If the humidity exceeds this threshold, there is a risk of sugar bloom, a white dust that forms when sugar dissolves in moisture and then recrystallizes on the surface. Conversely, if the humidity is too low, especially in dry climates, the chocolate can become brittle or develop static electricity, which can affect the quality of the product. The storage system is designed to ensure airflow between pallets, helping to maintain an optimal storage environment. Each pallet is tagged with a unique identifier and scanned into the warehouse management system, allowing each batch to be tracked, its location, storage time, and next destination. If quality control is required before distribution, a sample group is selected for post-production testing. These tests may include shelf life simulations, in which the chocolate is exposed to different environmental conditions to assess stability over time. Texture analyzers can test for crispness, while gas chromatography helps determine the stability of volatile flavor compounds. Once the product has passed inspection, it is scheduled for shipment. Whether it is being shipped to a distribution center, a specialty retailer, or for international export, the chocolate must be stored under strict conditions similar to those at the factory. This may require refrigerated or climate-controlled trailers, especially for premium lines or products that are sensitive to high temperatures. During hot months, some companies delay shipments until night or use pallet insulation to reduce the effects of temperature during transfer. Vehicles are often equipped with battery-powered temperature recorders to continuously monitor environmental conditions. When the goods arrive, this data is checked to ensure that temperature and humidity remain within acceptable levels. If any discrepancies are detected, the recipient has the right to reject the shipment even if the outer packaging appears intact. This level of accountability ensures that product quality is always closely verified. At the point of sale, chocolate continues to be exposed to environmental factors that can affect quality. Supermarkets or convenience stores sometimes place chocolate in unrefrigerated locations, which exposes it to light, temperature fluctuations, and air conditioning systems. To mitigate this risk, factory teams can conduct in-store audits or through contracted merchandising specialists. These audits focus on product placement, stock rotation practices, and the quality of products on display. In addition, manufacturers conduct testing by purchasing random samples from stores and sending them to a laboratory for analysis to assess the stability of the product over weeks or months in the distribution system. The results can help refine shelf life parameters, improve packaging, or adjust emulsifier ratios to increase temperature resistance. While the production process follows a strict system, flexibility is built in to meet market demands. Many factories operate small batch production lines, allowing for experimentation with new recipes without disrupting mass production. Even with limited production, roasting, refining, conching, tempering and packaging are still performed with great precision, but in a more flexible format. The journey of chocolate from tropical farm to factory and beyond is a delicate transition where each stage plays an essential role. From fermentation to develop the flavor precursors, to roasting to unlock complexity, to creating a smooth finish, each step is part of a marriage between precision technology and food artistry. Each package is printed with a batch code, production date, facility code and expiry date using high-speed printing technology, allowing for full traceability. The robotic arm then places the packages into cartons, seals them with glue or tape, and arranges them on pallets in the most optimal pattern for shipping. The pallets are wrapped in stretch film, labeled with shipping barcodes and inventory data, and transported to the warehouse consolidation area. Mars, Incorporated is one of the world's leading confectionery manufacturers, with a diverse product portfolio distributed worldwide. Mars Wrigley, the confectionery division of the group, owns many famous brands around the world. Key products include M&M's, sugar-coated chocolate balls in a variety of distinctive colors, Snickers, chocolate bars with caramel, peanut, and nougat fillings, Twix, crispy biscuits with caramel coating and chocolate, Milky Way, soft chocolate bars with nougat fillings, Skittles, colorful fruit candies with crunchy shells, Dove, Galaxy, premium chocolate with a smooth texture, Orbit, sugar-free chewing gum with a variety of flavors. Mars Wrigley exports confectionery to major markets such as the United States, Europe, China, Japan and Australia. The group also expands its operations in Southeast Asia and Latin America, where the demand for confectionery is growing rapidly. With advanced production systems, Mars ensures consistent quality globally, bringing attractive products to consumers everywhere.